All right, hopefully you are here to hear about simulation in Python using the package SimPy. They told me to be as loud as possible, which is not a problem that I have. So hopefully you can hear me, and if not, make a wave or something, and I will try to do better. The materials for today, so this deck that we're looking at right now, you can find it at the first URL, and then I put up the Python notebook, both on GitHub and it's available on Google Colab, and I've already run it, so if you want to look at it right now, play along, feel free to do that, and of course it will be available forever after on the internet for your reference. What is a simulation? So if you read my little description, my little blurb for this talk, hopefully you knew that you don't need to know anything about simulation to show up, because I promised to define it for you. And now we've come to that time where I will tell you what a simulation is. Simulation is a way to solve a decision problem that we can't easily solve some other way. That's super helpful. And what I mean by that is maybe we can't collect enough historical data, we can't solve a closed form solution in order to make a decision about actions that we should take in our system. And so what we might do, if we can't collect all of that data, is to use a simulation to emulate that behavior. So it's sort of like faking information, using computers and the power of probability and the magic of mathematics. We were able to then build a model of the system that we're interested in and be able to see how it behaves, maybe when we change some inputs, when we change constraints, and that will give us some information in order to make any decision that we might be interested in if it's based on the performance of a complex system. And then I say here, my last bullet point, from the outputs of the simulation, we can draw inferences. That is, make conclusions about the actions that we should take. There are many types of simulation, so that's very broad. And also, these three types are very broad categorizations. But at a high level, we have discrete simulations. And that means, so a simulation is going to be something that happens over time. Right? Because complex systems, they exist in time. Something is going to happen and something is going to happen after it. In discrete time simulations, we say that that time happens discretely. I don't want to over-explain it at the risk of over-explaining and using the word discrete a couple of times to define discrete. But discrete simulations, again, happen in deltas of time that are broken down, and it's always the same delta of time. And that's when our state changes. What is the state? State is anything about our simulation, anything about our system, any variables that describe our state or our system. Continuous simulation, when we use models of equations where timing is a little bit less precise. It's often used in ecology, apparently. Don't ask me about examples there. That's what it said on the internet. I'm not familiar with ecology, but I am familiar with economics, and so it is used there. And then we can add Monte Carlo to our simulations, and Monte Carlo is more probability on top of probability, and Monte Carlo basically just is about taking randomly generating what-if scenarios, drawing from distributions, and seeing how that affects our output. So a Monte Carlo simulation would be taking one of our other simulations and basically supercharging it by adding more probability on top of our system and using probability to change our inputs and see what happens to our outputs. Today, I can only talk so fast. I can talk faster than this, but for your sake, this is as fast as I'm going to talk, and so we'll only get to talk about discrete simulation. Specifically, we're going to talk about something called discrete event simulation, DES. DES assumes that our events happen at specified intervals. That means that our system, the variables that describe our system, don't get to change in between time events happening. So our variables change at those set intervals, and discrete event simulation, the event is an occurrence that could change the state of a system. So we're basically, I'm going to get into this in a little bit more detail, but we have entities that are existing in our system. They're going through these discrete bits of time, so from like time t to time t plus 1, t plus 2, and the state of our system can only change at those discrete points in time. So that's very high level, and you're like, can you make this more concrete? Yes, eventually. I'm getting there. But that is discrete event simulation at a high level. And generally with a discrete event simulation, we use what's called a next event time advance. Yeah, there's a lot of jargon here, so if you don't remember it all in the beginning, you can always refer back to it. But next event time advance means that our variables, our state variables, again, remember state variables is just like what is happening in our systems, those are the variables that explain our system, are going to be updated at discrete points in time, and the clock is always moving one by one by one. Fixed increment time advance would be when that simulation clock, so this whole thing is about simulating a system, there's a clock that's ticking in the corner, right? Tick tock in the corner, that is our simulation moving along, and fixed increment time advance would be when we move the simulation clock on those fixed intervals. All right. Within discrete event simulation, so now we're going from the more general to the more specific. We started with simulation. There are many, 3 types we talked about. Within discrete simulation, we talked about discrete event simulation. Within discrete event simulation, I'm specifically going to show you an example of queuing theory. So other things you can do in discrete event simulation, we're specifically going to talk about queuing theory. Queuing theory is a branch of operations research where we use queuing theory to make decisions about the number of resources we need in order to provide a service. Okay, so we're going to simulate some sort of complex system where we have entities that are resources that are using some sort of service or server, and we're going to try to find out how many of them we need. So canonical example might be bank tellers. How many bank tellers do I need, depending on the amount of customers I have coming through my branch? If you are of Generation Z, I don't know if you're familiar, there used to be these buildings where you would go and you would interact with people in person to transact money. But the queuing theory was originated by, I'm going to not do a good service of saying his name, but Agner Krarup Erlang. He did this in the 1950s. He created models to describe the system of the Copenhagen Telephone Exchange Company. I got that from Wikipedia last night. I always try to add a little bit of historical interest. But basically queuing theory here, as demonstrated or illustrated by this schematic, we have some sort of entities, customers coming in through our system. They're arriving to a queuing node. Within the queuing node, we have different servers, and so they may get service at one of those, and then they're going to depart our system. And that is queuing theory. Little bit more technical flourish here. So within queuing theory, we can write it in what's called Kendall notation. That was defined in 1953, originally with just 3 factors describing. So this is a way to describe a queuing system, okay? Called Kendall notation, specific to queuing systems, and you would define it using the letters A, S, and C. A tells you the time between arrivals to the queue. So that's the thing in the middle, that queuing node. How often are customers showing up to my bank, to my store, or how often are my machines breaking down? That could be an example if I have machines that break down and they require service from a technician. Those broken machines would be my customers arriving to my queuing node. So A is the time in between those arrivals. S is a service time distribution. So that would be how long it takes to provide service at a node. So if I'm calling in to a call center and I'm on the phone for 8 minutes, that would be my service time. And that, of course, is drawn from a distribution. C would be the number of channels that are available to us at that node. So in the previous schema, we saw A, B, and C, and those would be the available service for us at each queuing node. Okay. Yeah, go for it.
So is S the only random variable, or is it like time from now it's going to be fixed? Is that it?
Well, let me get to my next page. So I think, yeah. In the time you ask the question, I prepared the next page, and I think you're going to like it. Okay. Would we like more theory? Yes, more theory. Good, because I have more theory for you. Thank you for the question. And so the simplest type of queue that you can work with, that we're going to work with today, we're going to put this into code, is called the MM1 queue. And what M means, so there are different letters, and you can look this up, there are tables that explain the different distributions. But what that first M means is that my arrival process is a Poisson distribution. That means that the time in between the arrival of each customer, how often my machines break down and require service, we're pulling that from an exponential distribution. And then M would be the service time, and you could make that fixed. If the amount of time it takes to do the service is always fixed, you absolutely can. But in this MM1 queuing system, that actually we're going to pull that from a distribution too. So that's also going to be stochastic, and we're going to pull that from an exponential distribution. In general, this is just like what's standard to be used for arrival times, and there has been some empirical work to line up actual arrival times in different complex systems and have it match up to these distributions. And so the exponential works quite well for a lot of applications, but of course I'm being very general here, and you may have a specific application where you may need to use a different distribution. But in the MM1, the two M's are both going to be these exponential, or draws from an exponential distribution. And the 1 here just means that I have a single server. Some other theory that I didn't quite get into today that you can, if you want more of this, you can read more about it, is whether that single server has a finite or an infinite queue. In our case, we're going to, when we code this up, in a moment, we're going to let that server have, an infinite waiting area and let as many people come into the bank as possible. And hopefully nobody calls the fire department on us, but we're going to get away with it within our code example, hopefully. What questions do we have about this? Cool. All right, so some of this I already said in the prior page. I just wanted to clearly lay out what the M and the 1 were, but we have arrivals that are coming at a rate lambda. Lambda is just the variable we often use to refer to a Poisson process. And when, customers or jobs arrive to our simulation, then they're going to move through different states in our simulation. And so that would be like they can visit different servers if we have those in our simulation. Here we just have the 1. Service times, we said exponential distribution. If you need the Greek letter for it, that's going to be mu. So 1 over mu is the mean service time. Arrival times and service times are assumed to be independent. I don't know, does that seem like a fair assumption to make in the real world? How many people are coming in to get service and how long it takes my server to do the job? And that's kind of a trick question. I have some people shaking their heads, no, that's probably fair. Maybe if it's like a human who's doing that service and there are other frictions that happen. You know, if you have 100 people in your restaurant and we can't like seat people around them, then that wouldn't be fair to assume that they're independent. But maybe if it's machines that are doing the service, then we can assume that they're independent. All right, a server serves one customer at a time from the front of the queue. So that's going to be the first come, first served. And service is complete, the customer leaves the queue, the number of customers in the queue is going to be reduced by 1. Here in the MM1 queue, I said the buffer is of infinite size, so we can have as many customers queuing up as we may desire. Okay, now we're going to get closer to how we talk about this in code. So within our MM1 queue simulation, we're going to have 3 types of things. The first one is the entity. And the entity refers to the thing, great word, great descriptive word, I know, the thing passing through the simulation. So it could be a customer, a widget, a car, like I said, it could be a widget if it could be an item, not a person if it's something that requires service like a machine that has gone faulty and we need to fix it. Every entity that passes through the simulation is going to have attributes. Attributes are just going to describe things like the preferences or maybe like the type of engine that has come in for service. And the important thing to know about those attributes is that they also have a priority. So we'll set a priority in our code, but maybe we have like VIP customers and normal customers, or maybe in our grocery store, we have a line specifically for people who have 10 items or fewer, and maybe they get to go into a priority queue. And so that would be one of the attributes of the entity. Entities are going to track their own journeys through the simulation, so they're going to keep track of information about themselves as they move through our system, including the time that they had to wait for a resource and the processing time. So if I call the help desk, I'm definitely going to know how long I had to wait, right? And when I get to finally have my problem fixed and I get to leave the simulation. The resource. The entity is going to request service from a resource. Within the resource, we have a capacity. So within the resource, the capacity is the number of entities that can receive service simultaneously before I start having a queue. In our example, we're just going to have capacity of 1, but once you take this example and you play with it and you're extending it, you can see what happens when you change that capacity. And then we don't just have to have a single resource in a simulation. So you may have, different resources all within the same simulation. So if you have like an assembly line and you have some sort of widget that breaks and first somebody needs to like take apart the engine and then somebody else is going to do a diagnostic test and then somebody else is going to replace the broken parts, those would all be different resources within our simulation. The source. The source is sort of like the god of our simulation. The source is what creates the entities that get to flow through our simulation. So the source is going to know information about like the attributes that I should create for every entity, what priority should I give them, what preferences might they have, and then the source is going to be the one that feeds those entities into my simulation. The source will also be the one that defines how frequently my entities are showing up, right? If we have my customers who are arriving to my grocery store, do they come every 5 minutes, every 10 minutes? That's going to be something that the source knows, because the source is the one creating the entities for our simulation. And as I said previously, the M, right, means that we're drawing from a distribution, from an exponential distribution, but abstractly, that inter-arrival time can be either fixed or drawn from a simulation. More jargon, more theory, time for code. Hopefully it's time for code, yes. I forget if there are any pages after this, but kind of hoping it's time for code. What questions do we have on the theory so far? Yeah?
Can I ask a question?
Yeah.
Since you talk about the discrete event simulations, but MM1 is a continuous time model, why don't you use a discrete time model instead of continuous time?
I didn't quite hear you. Why don't we use, so within discrete event simulation, I was saying there's queuing theory.
Yeah.
So there are other types of discrete event simulation that are not queuing theory.
Yeah, so MM1 is a continuous time queuing model. But
Yeah.
I was wondering why don't you use a discrete time queuing model, because you're talking about discrete.
Oh, well, because it's easier to simulate with continuous numbers than it is to simulate with discrete, just because of like the back end solving of the simulation. Yeah. Great. Other questions? Yeah.
Remind us, so what's the end goal going to be to figure out how long we're going to, how many servers you're going to need?
Yeah. Yeah. Wait, you didn't enjoy the theory just for the sake of the theory? You want an output? Yes. So in general, you would, right, exactly. You would be changing the parameters of your simulation, and I'm going to show you some of the metrics that you would measure, and then you're going to be changing the parameters of your simulation. Number of servers could be one of them, and you would look at the wait time. So you would be like, when Lara calls Bank of America, is it okay if she waits for 18 minutes? Or should we, make her wait for only 10 minutes? That kind of thing. Yeah. I don't bank with Bank of America, so that was not like a dig on that fine institution. All right, so we're going to be using SimPy. SimPy is the package in Python we will use for discrete event simulation. SimPy is written in Python, Python-based, object-oriented discrete event simulation framework that describes the flow of entities through a complex system. That's really convenient because we just talked about the theory of describing the flow of entities through a complex system. Within SimPy, we're going to see these words again: processes, entities, and resources. And here I gave you some real world examples of what processes, entities, and resources could be. And I've linked to the source that I got these real world examples from. Is a great Medium post that you should read if you want more information. So processes that generate entities like customers, messages, computers, or patients, vehicles, machines, repair work in manufacturing, and then supply-demand processes for inventory. Resources would be servers, counters, emergency rooms, repairmen crews, tunnels for limited capacity congestion points. So that is, if you need to put things into a real-world context, I don't understand that, but if you insist, this person has done the work, and here are some examples for you. So, speaking of theoretical, once we do our SimPy simulation, there are some, you can compare the SimPy simulation to what would be the theoretical metrics from our simulation, our MM1, and see if the outputs that you get actually align with this. So this is going to be your homework. This is the takeaway. You're going to, after you run the simulation, going to take the outputs from that simulation and calculate these things, and then you're going to send me a message on LinkedIn telling me whether you were able to match up the theoretical to the simulated metrics. Okay? All right. And these are a couple of real-world examples, so I lost interest when it came time to find the third one, hence the empty bullet point. But I did find you two, and these were actual papers that are written about how to use discrete event simulation and queuing theory in the real world. One of them is about the number of hospital beds to have, and then I think the second link shows you a bunch of different articles that in scientific journals that talk about using this methodology. Sources and suggested readings, so those links exist for you. Okay. I don't know if you have cool places to be in 10 minutes. They told me that I didn't quite have to end exactly at 5, and I may have internalized that. So if you have to leave at 5, I'm not going to be offended. But let's do the code. Okay, we're going to write a very simple model in SimPy. Yeah, go for it.
Do you have the link yet?
Yeah, for sure. So you can either download it from GitHub, or you can go to the Collab notebook. I don't want to change tabs. I'll give you guys a second. All right. Everybody have the URL? Great. All right, so a simulation has 3 types of objects: entities, resources, and sources, and we're going to now define those in the code. The first time that you run this, you may have to install SimPy in SimPy helpers. SimPy helpers, as its name implies, is a package that makes the process of getting statistics out of the simulation much easier. I will say, I use this in the real world. I knew the person who wrote it. He wrote it as helper functions for a course we were both TAing for, and I've actually used it in my job. So I recently refactored somebody's code at work and tried to bring in SimPy helpers to make that code a little bit more understandable. So I'll say I did use that in the real world, but we've got SimPy and SimPy helpers. So we're going to import those, and we're going to use NumPy to draw from distributions. The first thing that we're going to do is, of course, specify the constants we're going to use in our simulation. Depending on your level of familiarity with Python, right, the reason that they're in all caps is not because I am shouting at you what the values are. It's just standard to use all caps for constants. And you would normally put them all at the very top of your notebook or of your script. So these are numbers that you can then play with later and see how that affects the outputs from the simulation. The first thing that we're going to do is to define the entity class. The reason that this code is working this way and is quite simple is because of SimPy helpers. And so when I say, sorry, I hate when people scroll back and forth, but I forgot to tell you that from SimPy helpers we were importing entity, resource, source, and stats. And so those first 3, we're going to extend those by defining our specific classes for this simulation. So that's where entity, resource, and source come from. And then at the very end, we'll use stats to get some information back out about our simulation. Our entity class, remember our entity, this is the things that are passing through our simulation, so our customers, our widgets, whatever it may be. And I'm calling my class process entity because this is going to be the code that actually does the processing once my entity enters the simulation. So I haven't quite yet defined the source yet. I'm defining the entity first. Once the entity arrives, this is how it's going to flow through the simulation. And so process entity is what I call my class, and that's being extended from entity, which again is defined in SimPy helpers. And because we're doing that, we have to, in order for the whole thing to work, we have to define a method called process. And this tells us how my entity is going to be processed. Yield, you may be familiar, in Python means that we are using a generator. And so if you're not familiar, you're going to later be Googling generators in Python. And what that means is basically a function, but a function that is stingy and only returns to you one item at a time. So you probably have seen a generator without even knowing it. Like if you used a for loop and you said for I in range 5, that range 5 was actually a generator. It didn't return 0, 1, 2, 3, 4 all at once. It returned 0, and then the next time it was called, it returned 1, etc. So that is a generator, and that is what the yield statement means instead of a return statement. So we're going to yield self, of course, that's just like the way that we can reference our object, is going to wait for the resource, and of course, my resource, we're going to define that in the next step, but first, why not do it in this order, right? Just to talk about the way that we're going to process the entity first. And so my resource, we will define the resource in a moment, but the first thing we're going to do is wait for the resource. And when we get to the resource, what will we do? We will process at the resource. When we define the resource, we'll see that is where we get to say how long service is going to take at my resource. But this code is about the entity and how the entity is going to get processed. So after I wait for the resource, and when it's finally my time, I get time with the resource, I process at the resource, I'm then released from the resource. Remember we said when processing ends, you leave the resource and then you free up space for the next entity to be able to use that resource. And then, of course, once we get to the very end of process and it completes running, that means once the process ends, the entity leaves the simulation. So I'll be able to get metrics on things like the time that it took to be served at the resource and also the time that I spent in the simulation from the moment that I was incepted by the source God until I left the simulation. Okay, that is entity. We okay with that? What questions do we have? No questions. Perfect. Resource. Resource, remember, is where my entities are getting served. And so what we have to, again, because we are defining it, we are inheriting from the resource class, defined in SimPy helpers, in order to make just the whole process of getting statistics easier. That's why we do this. Otherwise, you could write these, could write these functions in classes however you wanted, and then it's just a little bit more complex to get the stats out. But within my resource, what the minimum that we have to define is the service time. And I said we could define this as fixed or stochastic, and if we're using stochastic, we'll often draw from an exponential. So our good friend NumPy is going to give us a draw from the exponential, and then the lambda is going to be that mean service time, which, as it's in all caps, reminds us that that was a constant we defined at the beginning of the simulation. And so what is the mean service time for this simulation? I've already forgotten, so somebody has to shout it to me. 20, I heard 20. Hopefully that's correct. Thank you. The source class, of course, is going to be what is generating my entities. Here I called it generate customers to make it a little bit more concrete. That is from our source class, and that has a minimum 2 methods in it. So inter-arrival time would be the time between, as its name implies, between each entity arriving. That's going to be returned from an exponential. mean time between arrivals, also a constant. And then this method, build entity, is going to be the method that creates all the entities for my simulation. Remember that an entity has attributes, and so here we make attributes a dictionary, and we're going to, maybe one type of attribute is going to be the customer type, and here within our customers we're going to have a standard customer and a priority customer. Just depending on how much I personally like that person, it will be assigned. No, it's from a random choice from NumPy, standard, or priority. And the reason this matters, because I remember I told you that within these types of queuing theory models, we had the priority queue. And so we define the priority of our entities entering the simulation. In here we say if the customer equals a priority type, and this priority is just coming from here, either standard or priority, then I set the attribute of priority to 0. Setting the attribute priority is something that SimPy helpers knows about, and that's why I can say attribute priority equals 0. The default priority is 1, and then the lower the priority number, the higher priority that entity would be. And then here, remember we defined process entity in the first step, and so that we're going to be processing our entity after we build the entity. All right, we can do this. We've got like a few more minutes, and now we're at running the simulation. So we're going to set a random seed. I ran the simulation twice, once with the random seed 34 and then with the random seed 35. Today I'm 34, tomorrow I will be 35. That is why I chose those.
Happy birthday!
Thank you. So env is the standard name that people will use for the variable that sets up the environment that's going to be running our simulation. Remember, we imported SimPy, and then within SimPy, we're going to be creating an environment that's just how you use SimPy to run your simulation. You have to create that environment. We create then my resource. I gave it the super intelligible name, my underscore resource. That uses the class I defined, my resource up above, pass it in, the environment, and then capacity. And remember that this is inheriting from the resource class from SimPy. Capacity means, anybody remember what capacity means? It was one of the like 600 jargon terms I defined for you, but capacity is the number of entities that can receive service simultaneously before a queue starts to form. And it's helpfully been written here for you in a comment. Generate customers. This is where we're going to be creating the number of entities that are running through my simulation, the number of jobs, whatever it may be that's going to come through my simulation. So that's going to be entities. And then kick off the simulation, env.process. That's just, again, how you use SimPy to kick off a simulation. My source was my source that I just defined right up here where I generated my entities, .start, and then debug is false just because we don't want to write out all the steps. You can change it to true yourself and see what it prints out, so that can be helpful for debugging. We're going to set it to false here, and then env.run, run the simulation, exclamation point. All right. So it looked like it ran, didn't give me any errors. My simulation has completed. So what the heck happened? I can use stats to get, so remember stats class comes from SimPy helpers. I can use that to get information back, statistics on the simulation. So for example, get total times would return to me the total time every entity spent in the simulation. So here I just returned to you the first 5. And these are the first, the total number of times that were spent in the simulation. So you might be like, what time units is this in? The time units are just in the units of discrete numbers. And so you can use things like, I'll often use PyArrow or any date-time library. And if I want to do a simulation over like a calendar amount of time or a clock amount of time, I will set my 0 point, and then I can use like a date-time library to do some just calculations, just some arithmetic to find out if it has been 60 units of time. I'm going to say that means that 60 seconds, and then I can translate that, and I can set a starting time of like January 1st, 2020, and if it has been, 600,000 units of time since the start of my simulation, I could just do arithmetic to figure out what calendar day it is. And so I haven't done that here. That's just like the next step of complexity. So if you're like, how do I turn these numbers into calendar times? You could do something like that. But here, I just want to show you the things we can get out of stats. So we can get the total times, and here I'm running the mean on all of these. So total times, waiting times, and I'm processing time. So in my simulation, total time, 99. Waiting time before, I got to a resource and was served. And then, of course, processing time, so this is how long you're on the phone with the help desk, was 33. I can also, because I set a priority, I can get the customer average waiting time, standard versus priority. Okay, thankfully, that worked. I forgot to check, but thankfully priority is a lower number, and so it appears that it did work, and those customers we set to priority had a much lower waiting time. And then this is the processing time on average. We already saw that one. We can do things like here I've used Seaborn just to do some plotting. So this is a histogram for time in simulation, and this is the count of the entities. I believe we ran 200 entities through, and so it looks like most of them, sorry, it's 5 o'clock. This is a histogram of the number of entities that waited this amount of time units. We've got the waiting time per entity, so this was the waiting times. This is the queue size over time. And then the only thing that's left, I reran it using a different random seed, and then you can just like compare the outputs to see that they've changed. And of course, you can go through and change the constants for a simulation, change the capacity, and see how the simulation would run. So that is what I've got for you on simulation in Python using SimPy. I'm happy to stick around if you have questions, but I won't hold everybody else up, so thank you so much.